Yeah, I'm going to talk to you about uncovering the origins of the universe with neural networks. So I'm a PhD student at Bristol as well, and I work in radio astronomy, looking at observations from the early universe and trying to understand what happened then. So to kick off, I'm going to sort of ask just a kind of couple of questions to get you thinking about what happened at the start of the universe. So how old is the universe? How was it created? What size might it have been at the start of its creation? So the answer to the first question is, it is 13.8 billion years old. That is the sort of current accepted age of the universe. And it started with the Big Bang, which I imagine a lot of you have probably heard of. The kind of description of Big Bang, I think, is always a bit misleading because it makes it sound like an explosion, and I don't think there was necessarily an actual explosion. But it was a point there was a point that was, I think, the current sort of lower limit on the size of this was about 17 centimeters, which is approximately the size of a football. And all of the matter and energy that exists in the universe today was compressed into this really small place. And so, as you can imagine, it was very, very dense, very, very hot. And there was a lot of pressure inside of that. So from here, the universe inflated really, really quickly, like exponentially quickly. So I'll show you a diagram of this, and you can see at the kind of start point of this, you've got the Big Bang, and as I say, the really rapid inflation up to this area. Let me just move my pointer, where you can see the green part, that's the cosmic microwave background. So that's like a relic of the Big Bang. So we can observe what happened there with that. And then the universe starts to inflate a lot more slowly now because of the matter that's in the universe. It's starting to aggregate together to form masses, and the gravity of these are acting as a sort of counter to the expansion of the universe. So it slows down. Now we're kind of seeing an accelerated expansion, which we think is due to dark energy, but that's not what I'm interested in or talking about today. I'm interested in the period that happens just after the Dark Ages. The Dark Ages, basically nothing really happened for 400 million years. And then the first light sources were born. So when we have all of this gas in the universe, they start pulling together to make, bigger clumps of gas. And then eventually when they get massive enough, there will be a kind of pressure that's trying to make it collapse in on itself. And that will become high enough that we will have temperatures high enough that we can ignite nuclear fusion and create a star. So we have these very first stars that exist in the universe, and they interact in a certain way with the other gas, dust, and stars around them. So this kind of era that I'm looking at is called the epoch of reionization. And the reason it's called that is because the space between these stars is predominantly neutral, made up of something called neutral hydrogen. And over time, these stars will emit ionizing radiation, which will change the state of the neutral hydrogen to an ionized state. So that's a really important thing to note about this era, because the stars that existed at this time produce, light that has to travel a long way to us. So we can't directly observe those light sources. And, that light is far too faint for us to be able to actually observe these days. But because of this abundance of this neutral hydrogen that exists in this early universe, and the fact that it interacts with the early stars, we can kind of indirectly observe this era by observing the neutral hydrogen. So there's an interesting characteristic of this neutral hydrogen in that when it changes state, when ionized by radiation from a star, we have the electron and proton that exists in the hydrogen, and they have something called spin. And in its neutral state, they spin in the same direction like this, like parallel, they spin in this way. And then when ionized, the electron spin flips the other way. This is called antiparallel. So when we change between the parallel and antiparallel state, it emits a photon. And that photon is what travels across the universe to us to observe. And as it travels across the universe, it becomes stretched out due to something we call redshift. And when it reaches our eyes or our telescopes, it's observable at 21 centimeters, which makes it in the low frequency radio band. So we can look at it with radio telescopes. And so the way we kind of think about it now is we've got this neutral hydrogen that we can observe how it interacts with the stars around it. And then by that, we can kind of indirectly observe how these stars change and how they interact with each other in the space around them by looking at different snapshots through time and seeing how this kind of map of neutral hydrogen and ionized hydrogen changes. So I like to think of it as like a block of Swiss cheese. So the kind of cheese part is the neutral gas, and the holes are the ionized gas that are surrounding the light sources. And over time, these kind of holes will change and grow. And that's how we can observe how this period of the universe was evolving and changing. Okay, so I mentioned that we can observe this with radio telescopes. So there's just a little diagram here of the electromagnetic spectrum, which you've probably seen before. And we're interested in the radio band, which is on the kind of far right side of that very low frequency. So then underneath that, you can see there's a picture of a telescope. This is the Lovell telescope, which is at the Jodrell Bank Observatory in Cheshire. And this is used to observe low frequency radiation from space. So once we have this radio telescope, we can then think about how we can apply this to our bigger problem. And this is where the SKA comes in. So the Square Kilometre Array, or SKA, is currently being built in Western Australia and South Africa, and it's going to be the world's largest radio array. And it's going to be up to like 1,000 dishes and up to 1 million antennas. It's going to be really, really big. It's going to be literally a square kilometre of telescopes. And they all connect together through something called radio interferometry. And this means that we have a huge collecting area for a dish. So it means we can collect loads and loads and loads of this radiation. And by doing this, we can have a really deep survey into looking back through space. So the SK is going to be one of the most sensitive probes for looking at this. Also though, because we've got such a big telescope and it's going to be collecting a lot of data, it means that the telescope is going to be collecting data at a rate of 160 terabytes per second. To put that in perspective, 1 terabyte is about 500 hours of streaming on like Netflix or something. So if you were to binge watch Netflix for 24 hours a day, for 7 days a week, that would equate to nearly 500 weeks worth of Netflix binging. And that is the data that's going to be coming out of the SKA per second. So it's a very, very big data problem. Here's just an artist's depiction of what the SKA might look like. But as I say, yeah, it's just a lot of radio telescopes all in a big desert. Okay, so where are we now? We know what we want to look at and why we want to look at it. We have a method of observing this kind of cosmological era through the 21 centimeter signal. We have a telescope that's sensitive enough to detect the signal. So what are going to be the challenges going forward? The main issue that we face is the fact that the signal was generated billions and billions of years ago. So it's traveled a long way to get to us and has encountered a fair amount of interference. So we have to account for the interference that it's had, so absorption and emission through gas and dust and other sources. And also is a very, very faint signal. So when we're looking back through time, we're looking out from Earth and our telescopes, we look through our galaxy. And in our galaxy, there's lots of radio sources, really bright ones. We look through other galaxies. There's lots of really bright radio sources, like Robbie was talking about, AGNs. They can emit radio waves. So there's a lot of interference. We call this contamination. And this is something that we have to be able to disentangle from the actual interesting cosmological signal we're looking at. In this picture, there is just a very, very small snapshot of what some of this data might look like. It's a very tiny little section of, one of these big images, but you can see there's quite a lot of variation of types of sources. And this is actually an image that's had the signal, sorry about that, signal to noise ratio increased. So these look a little bit brighter. But a big problem we have is that the background noise and the signal are quite hard to disentangle from each other because they're very noisy images. So what can we do about this? I think to answer that question, I want to ask a question, which is what do all of these images have in common? And the answer there is machine learning. So machine learning is like prevalent in our daily life. You know, it's on social media, Instagram, Facebook, Pinterest, those kind of things. And it's used to have algorithms that give us the kind of content that it thinks we want. It's in our phones, with our Google Assistant, with Siri. It's in maps, being able to predict how long it's going to take to get somewhere. It's in the emails we send. It's in, you know, the email servers predicting which emails get piped to spam. So how is machine learning useful in our case? So machine learning is used really widely on image data. That's kind of including like facial recognition and self-driving cars, things like that. And how can we use it here? It can be used to classify objects within an image. So if we give it an image, it can tell us, you know, what's in this image. And it's also very, very useful at processing large amounts of data, which is obviously going to be useful here. As I said, we've got really lots and lots of data to get through, and we can do that with machine learning in an efficient and automated way. And then once, you know, we're able to classify and detect the sources within the data, we can then take them and have a look at the interesting science that's behind them. And in some, you know, interesting cases with machine learning, it can tell us about sources that we didn't necessarily know about. So that's a really kind of exciting avenue. So this is just a little bit of a diagram of a very kind of basic neural network that might be used for image classification. This is something called a convolutional neural network, which is just the type of functions that are performed on the data that we pass to it. So the way this would work is we would provide it a training set of data. So we take our big image that I showed you a little bit of that data before. We take the image, and in this case, we have labels. So we know areas in the image where sources exist. We cut around those, and we pass that into the network, and we tell it, here is a source. And it takes that data, performs its transformations, convolutions, and it learns information that's in the data. It learns the statistics about what makes a source a source. And we also give it information about not being a source. And it learns about what a source doesn't look like. And we give it loads and loads of data, you know, lots and lots of images, lots of sources, lots of not sources. Typically with machine learning, the more sources you give it, the better result you're going to get. And then once we've trained it and we're happy, we then give it data it's not seen. We give it another image and we ask it, is there a source in here? Source or not a source? And it will tell us a probability for both things. It'll tell us maybe, you know, I'm 80% certain that there's a source in here, and I'm 20% certain that there's not a source. And so this is, you know, this is really exciting to be able to potentially do this with machine learning, because we could kind of crunch down these huge data sets that we're getting to then pass on to, you know, other maybe networks or other types of astrophysical processing that might happen, that we can then kind of look at what's going on and hopefully be able to understand more what's actually happening during the early universe. So just to summarize, I talked to you a little bit about the start of the universe, the first light sources, and how we can use the 21 centimeter hydrogen signal to observe their evolution through time. I told you about the SKA and the fact that that's going to be a really big telescope that's going to help us hopefully look back at this period of the cosmic dawn to understand what happened. And that I am trying to use machine learning to take those images and actually produce some science out of them. So thank you very much for listening. Do you have any questions?
When do you think the SKA is going to be finished?
They keep pushing back the date. It was supposed to be like 2030 or something. It's gone back again. It won't be done before my PhD is over, definitely.
That always seems to be the case with these things. It takes forever to get them done.